All right, so there's a lot of like vocabulary and definitions that we need for to talk more about sets. So let's begin with what's called the empty set. The most basic set and simplest set you can imagine is a set with nothing in it. And as you can imagine, as you can probably guess, the notation for that is a set with nothing in it, right? It's like this is the empty set written in roster notation. There's nothing in there. But there's another symbol we often use for the empty set, which is like a 0 with a slash through it. Okay, some of my students will occasionally use this symbol to mean 0, which is a little bit confusing because we often use it to mean the empty set, and the number 0 and the empty set are very similar and they're related, but they don't exactly mean the same thing, at least not always they kind of mean the same thing in some contexts and different things in other contexts. So I just recommend that you reserve that notation for the empty set, not 0. So the next definition I want to go over is the idea of a subset. The idea of a subset. A subset is like some of the elements, but not necessarily all of them. If you write this notation, A, and then this kind of like sideways U, it's kind of like a C with a line underneath it. This is the notation that means A is a subset of B. And this is defined if and only if, for all x, if x is an element of A, then x is an element of B. Okay, so this would potentially include the entire set B. B is a subset of itself. It also includes the empty set because this becomes true vacuously. We'll go over that in a minute here. That's actually a theorem that's coming up. So that's our notation for subset. Technically, you could say A is a subset or equal to B. That's what that means. So this is sort of like the less than or equal to symbol. To distinguish that from, we want to distinguish that from the idea of a proper subset, which is technically a subset, but it's a special type of subset. So a proper subset is written like this. A is a proper subset of B, and that is defined by saying if and only if basically A is a subset of B, but it's not equal to B, and it's also not equal to the empty set. So it's saying, it's a subset of B, but it's not the whole set, and it's also not empty. So it's properly a subset, some but not all of the elements. That's what that means. So let's just go over a couple of examples using some sets. So I'm going to define A to be the set 1, 2, 3, 4, and B is going to be the set 2, 4. Okay, so using these definitions here, here's things I could write. I could write B is a subset of A. That's correct. I could also write B is a proper subset of A because it is some but not all of the elements, right? A is not a subset of B because there are elements of A that aren't in B, right? So you could say this would be false, right? Because you could say 4 is an element of A, that's true, but 4 is not an element of B. You'd get true implies false, which is false. So that does not satisfy the rule. What else could I write? I could write, let's see, A is a subset of A. It's a subset of itself, but A is not a proper subset of A. It's just a subset, not a proper subset. I can write that the empty set is a subset of A, and the empty set is also a subset of B, but it's not a proper subset of either of them. Okay, so there's just a few statements we could make, a few true things we could say here. Now I want to also make a point about distinguishing between an element and a subset. So the elements of A and B here are the numbers, right? So we could say 3 is an element of A, but 3 is not a subset of A. Okay, so 3 is an element of A, but it's not a subset of A. Now, if I wanted to talk about a subset containing just 3, I could write this. I could write it in roster notation with braces. That is a subset of A, like that. 3 is a subset of A, but that 3 with braces around it, that's not an element of A. Okay, so 3 is an element, and the set containing 3 is a subset. All right, that's the distinction. If you take an element and then you put it in a set by itself, that's called a singleton. This is called a singleton set. And it's different. It's different from the element itself. If you take the element by itself and the set containing it. So yeah. All right. So now let's talk about this theorem. A simple theorem. I've kind of already said it, but it's for any set A. Two things are going to be guaranteed. The empty set is definitely a subset of A, and the set A is also a subset of A. So every set always has at least two subsets. It's got the empty set and the entire set. Now, if the set A is the empty set, then these would be the same, and then it would be only one. But as long as you're talking about a set that has at least one element, then these would be distinct, two different subsets. So there's at least two subsets for most sets. Okay, so that's the theorem. We're going to use that information a little bit later on. So now we've been talking about things like equality of sets without really having defined that. So up here I'm saying not equals. We never really defined what equals means. So let's get a nice definition of that down here. Equality of sets. If you've done some programming, especially with data types, if you've ever written your own data type, happens in CS2, or sorry, CSI, I don't know what the number is here. It's the one about data structures. But when you write your own data type, you might say, okay, so here's a data type. It's going to be called a thingamabobber, right? And when you are creating that, you might need to write a definition for what it means for two thingamabobbers to be equal to each other, right? Because a computer wouldn't know what that means unless you tell it. So here's what it means for two sets to equal each other. A equals B if and only if for all x is an element of A if and only if x is an element of B. Like that. This is what it means. This is what it means for two sets to be equal. Now you'll notice that looks a lot like this one. So let me just put circles around these. That looks a heck of a lot like this right here, right? Look at the similarity between those. The difference is this is one-way implication. This is two-way implication, biconditional. So since biconditional can be written as like P implies Q and Q implies P, you can tell that in fact, another way to state this is to say A equals B if and only if A is a subset of B and B is a subset of A. So this is a strategy often used to prove that two sets are actually equal. If you take two sets defined differently, but if you want to prove that they actually have the exact same elements, you could prove that one is a subset of the other and vice versa, and that would imply that they are equal. So those are our starting definitions. We're going to do some more on the next video.